Welcome to episode 45 of The Explainer. Today, we're diving right into an absolutely incredible journey. We are going to track a single thread of logic from the microscopic hardware level all the way up through the vast network protocols of the internet, and finally arrive at a physical, real-world robot sitting right on your desk. It's a completely fascinating look at how we are actively bridging that massive gap between digital theory and physical reality. So, do computers actually process meaning? I want to challenge one of the most basic fundamental assumptions we all have about how our devices work. You know, when you type a prompt or ask an AI a really complex question, it intuitively feels like the machine actually understands the meaning of your words, right? Well, this is what researchers call the grand computational illusion. Beneath the surface, the machine doesn't understand your intent at all, literally not even a little bit. It only understands pure physics, resistance, and voltage. And to put that into perspective, get this, 80 to 90% of AI compute cycles, the heavy mathematical lifting that powers all of today's massive large language models, they are actually just hardware-level approximations. No way, right? But it's true. They aren't exact math at all. They are just highly educated guesses burned right into the silicon itself. So here is our roadmap for how we're going to build a flawlessly deterministic semiotic bridge. We'll cover 1. The grand computational illusion. 2. Gambler versus the Surveyor. 3. The HTTP 402 fracture. 4. The chopsticks design solution. 5. Enter the cheerbot. And 6. The FPU Switchboard. Let's get right into it.
Section 1. The grand computational illusion. If we want to physically automate the real world using digital inputs, we absolutely cannot rely on a foundation that is basically just guessing. Here's how it works. When you ask a processor to do complex, non-discrete math for an AI model, it immediately hands the task over to something called the floating point unit, or the FPU. The problem here is that chip manufacturers, like Intel and ARM, they use entirely secret proprietary seed tables to help that FPU guess the answer incredibly fast. And because this math is just an approximation, the exact identity and the provenance of the original data is permanently destroyed. Researchers actually call this the wood chipper effect. It's super messy. Actually, scratch that. It's more like a giant blender. You know exactly what fruits went in, but you can never, ever perfectly reverse engineer that smoothie back into its exact original components. Section 2, Gambler versus the Surveyor. To fix this massive accountability issue and establish verifiable trust, we have to look at two very different parts of a computer's physical brain.
Think of it like this. On one side, we have the FPU Gambler. It's fast, it's lossy, and it essentially just throws darts at a board to give you a really good approximation. But on the other side, we have the arithmetic logic unit, what we're calling the ALU Surveyor. The Surveyor deals strictly in deterministic, hardware-level absolute truths. 1 + 1 is exactly 2, every single time. And that's true on every single machine on Earth. So, by shifting our core logic away from the guessing gambler and over to the absolute truth of the Surveyor, we achieve perfect, reliable hardware determinism.
Section 3, the HTTP 402 fracture. Now, once we have that absolute digital truth locked down at the hardware level, we need a way to actually communicate it across the web. Okay, let's take a quick trip back in time. Back in 1996, internet pioneers actually reserved the HTTP 402 payment required status code specifically for native web transactions. But then, well, nothing happened. It literally gathered digital dust for almost 30 years. Why? Because developers kept trying to bind these bloated Ricardian contracts, these heavy, incredibly dense, text-based legal agreements directly to digital value transfers. It created this impenetrable wall of theoretical complexity that made scaling it basically impossible. Section 4, the chopsticks design solution. Let's look at the incredibly elegant fix to this 3-decade-old technical wall. I absolutely love this analogy. Instead of building a $1 million hyper-complex robotic arm just to pick up a single piece of sushi, you just use 2 simple sticks. That is the entire essence of chopsticks design. And the X42 protocol applies this exact philosophy to our 402 problem. Instead of building a massive monolithic smart contract system that drags around all that legal bloat, X42 acts as a simple webhook architecture. It completely bypasses the mess by relying on a beautifully straightforward client callback mechanism. So it breaks down into this really ingenious, simple callback loop. Step 1, the server returns a 402 status code demanding proof of payment. Step 2, the client's wallet signs a cryptographic proof of that payment. And step 3, the client retries the exact same request, handing over the receipt to instantly unlock the resource. It's an elegant, totally deterministic, event-driven loop that creates a total immutable lock-in. Boom, done. Section 5, enter the cheerbot. This is where the story gets really fun, because we finally burst out of the abstract network layer and directly into the tangible, physical world. Meet the Flow X42 cheerbot. This thing is a free, completely open-source alternative to a smart speaker, and it's wrapped up in this awesome 3D printed collectible desktop toy shell. Inside, it houses a little Raspberry Pi acting as a localized micro-host. But here's the kicker. It isn't just a toy. It is a fully functioning robotic vending machine that physically reacts to digital network tips. It absolutely proves that those X42 digital callbacks we just talked about can instantly manipulate the real world, and they can do it without needing any massive centralized intermediaries in the middle. Section 6. The FPU Switchboard. This is where the leaf nodes finally come alive, colliding both the digital and physical realms into one flawless execution. Historically, trying to map digital ledger data to physical hardware was a totally chaotic mess. I mean, one delayed signal could ruin the entire sequence. But the cheerbot, it acts as a physical switchboard. It reads a mathematically pure sequence of data, a last-in, first-out JSON state tree, to verify the exact truth. And once it verifies that truth, it directly triggers the physical GPIO pins, which are just those tiny little electrical connectors on the Raspberry Pi. So pure mathematical logic is seamlessly translated into electrical signals to do things like display a graphic or spin a motor. It's brilliant.
There's this great quote from the architecture documentation that perfectly captures what we call the semiotic bridge. It says, "The human pilot applies the intent, but the agentic cell executes the sweat," bridging that massive gap between messy human desire and strict deterministic machine execution. You see, humans are messy, we're associative, and we're probabilistic. But silicon, it's cold, it's rigid, and it's strictly mechanical. By using exactly formatted text and deterministic hardware, the human pilot applies the creative intent, and the deterministic agentic cell physically executes the sweat. We are quite literally tricking rocks into thinking with lightning to perfectly automate our imagination. So, as we wrap up this explainer, I want to leave you with one final provocative thought. We've traced this entire journey from the exact mathematical truth of a silicone surveyor through a brilliantly simple internet payment callback, all the way to a physical robot dispensing cheer right in your living room. We are entering a totally new paradigm where bit-perfect, absolute digital truth orchestrates physical reality. The semiotic bridge is officially built. The only question left is, what are you going to program it to do? Thanks for joining me on this explainer today. Keep learning, and I'll catch you next time.